Hello everyone, my name is Andrei Tankich. I'm a master's student from the Higher School of Economics in Russia. Today we'll be talking about asynchronous reconfiguration in the presence of Byzantine failures. This is joint work with Piotr Kuznetsov from Telecom Paris in France. The context of this work is replicated services. Consider a collection of servers that provide a specific service to a set of clients. To ensure that the state of the service is perceived by the clients in a consistent way, replicas are actively involved in a synchronization protocol. Typically, synchronization protocols are based on a failure model, a set of assumptions on who and where may fail. In a long-running system, to meet these assumptions, the set of replicas must be adjusted. Replicas that are suspected to have failed should be removed from the system, and new, fresh replicas should be introduced. This process is called reconfiguration. The most natural way to reconfigure a replicated service is to use consensus. When several reconfiguration requests are issued concurrently, the clients can use consensus to agree on the next configuration, and then transfer the state of the system to this new configuration. Early implementations of reconfigurable storage systems did rely on consensus, but it was later discovered that replicated services that otherwise do not require consensus can be reconfigured in a purely asynchronous way. More recently, a lot of progress was made in defining abstract asynchronous reconfiguration in a simple and efficient way. However, all these solutions assume benign crash failures only. The only comparable solutions tolerating Byzantine failures assumes a trusted administrator. In this work, we address the challenge of implementing an asynchronous reconfiguration protocol for the Byzantine fault model, where both replicas and clients may expose arbitrary or even malicious behavior. Our goal was to find a solution that would not rely on consensus or a trusted administrator. To get a sense of difficulties of Byzantine fault-tolerant reconfiguration, consider the following scenario that we call the "I still work here" attack. Initially, the protocol is executed by 4 replicas, and one of them is Byzantine. Then, through a sequence of reconfiguration requests, we eventually completely change the set of replicas. Perhaps because we suspected that some of the initial replicas were faulty. Due to asynchrony, it is possible that some clients haven't seen the reconfiguration change yet. One of them may then try to reach out to the initial set of replicas to learn the new state of the system. However, because this configuration is no longer relevant, it is possible that it is completely controlled by the adversary. In this case, the replicas may deceive the client and cause a violation of the safety properties of the distributed object. In theory, we could power off the old replicas or force them to destroy their private keys to make sure that they are non-responsive. This would prevent the safety violation in this case, but let us now consider a slightly more subtle example. It begins similarly. We have a system of 4 replicas and one of them is Byzantine. Then the system is reconfigured. But in this case, instead of completely replacing the set of replicas, we extend it by adding 6 new replicas. Perhaps because we anticipate an attack on our system and want to increase fault tolerance. Our new configuration can tolerate 3 failures, so it is possible that 2 more replicas become Byzantine. But the problem is that our initial configuration cannot tolerate more than 1 failure. Later on, when the client wakes up and tries to reach out to the old configuration, the 3 Byzantine replicas will be able to deceive the client. Note that we cannot power off the replicas in the old configuration, because we still need them in the new configuration. Therefore, an alternative way of dealing with such attacks is necessary. So we discussed the problems caused by Byzantine replicas, but Byzantine clients also have to be accounted for. The obvious attack for Byzantine clients is to issue a reconfiguration request to a completely compromised configuration. To prevent this, some access control policy has to be implemented. Another potential vector of attack for a Byzantine client is to interfere with the reconfiguration protocol to create a fork. The algorithm must ensure that this is also impossible. Before we discuss a reconfiguration algorithm that can solve these and similar problems, let me introduce a few important auxiliary abstractions. Let me begin with a quick recap of some terminology from the order theory. Consider any partially ordered set. An element of this set is called a common upper bound of 2 elements if it is greater than or equal to both of these elements. It is called the least common upper bound if it is smaller than or equal to all other common upper bounds of these elements. Finally, a partially ordered set is called a joint semilattice if for each pair of elements from that set there is a unique least common upper bound of those elements. In a joint semilattice, we can introduce a join operator, which will simply return the least common upper bound of its operands. An example of a joint semilattice is a collection of all subsets of some set, partially ordered by the subset operator. The least common upper bound in this joint semilattice is simply the union of the two sets. This leads us to the definition of lattice agreement. Intuitively, lattice agreement is similar to consensus. But instead of deciding on a single value, the participants must decide on possibly different but comparable values. Moreover, a participant can decide not only on a proposed value, but also on a join of several proposed values. Consider the following example. 3 clients execute lattice agreement on the lattice of subsets of the set X, Y, Z. 2 processes proposed singleton sets X and Y. The third process proposed the set Y, Z. Let us see what are the allowed outcomes of lattice agreement in this case. The first process could decide on the value it suggested, X. The second process could decide on the set X, Y because it is comparable with the decision of the first process and because it can be obtained by joining 2 of the proposed values. Finally, the third process could decide on the set X, Y, Z. What is not allowed is for one process to decide on the set X, Y, while another process decides on the set Y, Z, because these sets are not comparable. Neither is a subset of the other. Another situation that is not allowed is for any process to decide on the singleton Z, because it cannot be obtained as a join of several proposed values. But what is special about lattice agreement in the context of reconfigurable systems? Well, it turns out that resolving conflicts between concurrent reconfiguration proposals in asynchronous reconfigurable protocols essentially boils down to solving lattice agreement on a specific lattice that we call configuration lattice. A configuration, as an element of the lattice, is a set of updates, where each update is a pair of the type plus p or minus p, where plus p means that replica p has been added to the configuration, and minus p means that the replica has been removed. The members of a configuration are the replicas that have been added but not yet removed. Configurations can be compared using the subset operator and merged using the set union operator. In this example, each configuration has 3 replicas. However, one consists of only 3 updates and the other has 5 updates. Moreover, the first configuration is a subset of the second one. The next building block is forward secure digital signatures. As in normal digital signature scheme, each process can sign messages with its private key, and then anyone can verify the authenticity of those messages with the process's public key. The key difference is that the private key and each signed message are associated with epoch numbers. The process can only sign messages with epoch numbers at least as large as the epoch number of the private key. In this example, the client's private key's epoch number is 5 and can only sign messages with the timestamp at least 5. The process can invoke update key procedure and increase the epoch number of the private key. However, the reverse is impossible. Once the key is updated, there is no way to decrease the epoch number or to sign a message with a lower timestamp, even if the process later becomes Byzantine. Intuitively, you can imagine that each process has an infinite or a very long sequence of private keys, one for each epoch number. When the process invokes the update key procedure, it deletes all private keys from the sequence with timestamps smaller than the new epoch number. The magic is twofold. First, this sequence consumes very little disk space because it is generated on demand. Second, there is only one public key, which can be used to verify digital signatures for each of these private keys. One can obtain a forward secure scheme from any digital signature scheme by applying one of the many existing generic transformations. Let us now move on to the implementation of reconfigurable objects. There are several problems that we need to solve to implement asynchronous reconfigurable objects in the model with Byzantine failures. First, we need to make sure that the state of the object is consistently transferred between configurations. The idea here is quite simple. During the reconfiguration procedure, each replica of the new configuration contacts a quorum of replicas in some prior configurations. These replicas then respond with their current state. Crucially, when a correct replica replies to such a message, it promises that it will no longer serve client requests in the old configuration. If later on a client comes in and tries to perform some operation in the old configuration, the correct replicas that participated in the reconfiguration procedure will refuse to interact with the client. Due to quorum intersection, the client will not be able to complete an operation in the old configuration. Instead, the client will later discover the new configuration and will repeat its request there. But what if the replicas of the old configuration turn Byzantine? How do we force them to keep their promise even in that case? In other words, how do we prevent the "I still work here" attack that was described in the beginning of this presentation? It turns out that with the use of forward secure digital signatures, we can modify the state transfer protocol in a way that prevents this attack. We do so by assigning each configuration a number, corresponding to the number of updates in the configuration. We use this number as the epoch numbers in a forward secure digital signature scheme. We only perform state transfer from a configuration with a smaller epoch number to a configuration with a larger epoch number. When a replica requests state from an older configuration, the replicas of the old configuration update their private keys before replying. Thus, even if the replicas of the old configuration later turn Byzantine, they cannot recover their private keys for that configuration and cannot serve user requests. Due to asynchrony, it is possible that some correct replicas turn Byzantine while still retaining their private keys for this configuration. However, there will not be enough of them to constitute a quorum. So we'll learn how to deal with the "I still work here" attack by using forward secure digital signatures. But let me show you a more subtle attack, which we call the slow reader attack. Most storage algorithms are based on quorums. Let us first see how they work when there is no reconfiguration. When a client wants to store some information, it sends the data to more than 2/3 of the replicas. If later on another client wants to read the latest version of the stored information, it also contacts more than 2/3 of the replicas. The two quorums will necessarily intersect in a correct replica, and the client will receive the relevant information. Let us now see what can go wrong when there is a concurrent reconfiguration request. Consider the following execution. The first client simply stores the data on a quorum of replicas, as before. Then another client comes in and tries to read the data. It reaches two replicas. One of them is Byzantine and lies to the client, and the other is outdated. It doesn't have the latest version of the data and cannot send it to the client. The message from the client to the third replica is delayed. Meanwhile, reconfiguration happens. As we discussed before, all correct replicas in a quorum update their private keys and cannot reply to the client requests in this configuration anymore. However, due to asynchrony, it is impossible to force all correct replicas to update their private keys during the reconfiguration. Hence, one of the replicas can retain its private key for the old configuration when it is corrupted by the adversary. If the client's message reaches that replica, it will be able to lie to the client, and the client will finish its request with the old version of the data. Note that this attack is only possible when the client's request is concurrent with the reconfiguration. Moreover, it only applies to requests that read some data from the quorum. It does not affect requests that only store some information and do not read anything. But how can we address this attack? Well, it turns out that it is sufficient to add another round trip to confirm that the configuration is still relevant. The client simply sends a message to the replicas asking them to confirm with a digital signature that they still possess the private key for this configuration. Even if all replicas turn Byzantine, if the slow reader attack took place, then there won't be enough replicas to deceive the client. and the request will not be completed in this configuration. The client will eventually learn about a newer configuration and will simply repeat the request there. The next part is conflict resolution. Recall that when multiple reconfiguration requests are issued, in partially synchronous systems, the clients can use consensus to agree on a single descendant for the current configuration. However, in asynchronous systems, we have to resort to weaker forms of agreement. In particular, we will use lattice agreement. In this case, the clients will decide on different but comparable configurations. But this is not good enough. The clients cannot just perform reconfiguration to two different configurations, even if they are comparable. Therefore, we use the second instance of lattice agreement, this time on the lattice of sets of configurations. Each client will then decide on some set of configurations, and these sets are guaranteed to be related by containment. One of them must be a subset of the other. Moreover, in each of these sets, all configurations are comparable. This means that they can be viewed as sequences. The clients can then reconfigure the system according to these sequences. In this case, client 1 tries to reconfigure the system from the initial configuration to the orange configuration, and client 2 performs reconfiguration from the initial configuration to the merge of the two proposed configurations. However, the key idea here is that the second client knows about the orange configuration and will make sure that the orange configuration is deactivated before the merged configuration is activated. In this case, the two clients reconfigure the system through the same sequence of configurations. Another possible outcome is as follows. Client 1 can decide to go to the merged configuration via the orange configuration, and client 2 can decide to go directly from the initial configuration to the merged configuration. This may look like a fork, but in fact, both clients perform reconfiguration to the same final destination. It is guaranteed that replicas in the orange configuration will never serve any user requests. This configuration does not serve any useful purpose, neither it can harm anyone. The final part of the solution is access control. Recall that an obvious attack for a Byzantine client on a reconfigurable system would be to issue a reconfiguration request to a completely compromised configuration. To prevent this from happening, we need some access control mechanism. A simple approach would be to ask a trusted administrator or a quorum of administrators to approve each reconfiguration request with a digital signature, but this is too centralized. So what we can do instead is to ask a quorum of replicas to approve each request. This guarantees that each request is signed by several correct replicas, which can perform things like identity verification. Moreover, due to quorum intersection, this approach can be used to detect any potential conflicts between benign requests. Of course, additional steps are needed to make this work in a reconfigurable system, but the principle remains the same. To summarize, what we did so far over the course of this presentation is identified the challenges of asynchronous Byzantine fault-tolerant reconfiguration and discussed systematic solutions to each of these challenges. It takes an extra bit of effort to compile these solutions into a working protocol and to formally prove its correctness. For this, I invite you to read the paper in the proceedings of the conference and the extended version published on arXiv. Let me conclude with some open questions. In the design of these protocols, we were conservative in the sense that we assumed a very strong adversarial model. In our model, the adversary can compromise all replicas in a configuration immediately after a newer configuration is installed. Moreover, we assumed that the set of replicas can change drastically with each reconfiguration request and did not optimize for small and incremental changes in the set of replicas. This conservatism leads to perhaps more robust, but less efficient and more complex protocols. It would be interesting, therefore, to see what can be achieved with more optimistic assumptions. Thank you for listening.